Hello everyone, welcome back to my channel. Today is day 6 of solving GFG POTD, and today's question is shortest path in undirected graph. So let's solve this. The question says you are given an undirected graph having unit weight of the edges. Find the shortest path from source to all the vertex. And if it is unreachable to reach any vertex, then return -1 for that vertex. So from this given undirected graph, the source here is 0 and we need to find the distance from 0 to all the vertices, and we need to return the vector of distances. So the approach here can be different, like one can be done using DFS and other can be done using BFS. The time complexity and space complexity of both would be same, but the DFS approach would take redundant parts, so we'll stick to DFS for now. Then I'll also explain the BFS code. So the approach here would be to initially take the distance of each and every vertex as maximum value. Here we can take int max, and initially we need to create an adjacency list to track the node, which nodes are connected to which node. So the adjacency list of this undirected graph would be like this. So 0 is connected to both 1 and 3, and 1 is connected to both 0 and 2. So in this way we'll create an unordered map of int which is mapped to the list. So the adjacency list of this graph given here would be this, and initially we'll also take an extra space of vector having distances of each and every vertex initially, which would be int max. So the distance from source to that particular source would be 0, so the value of source would be 0 initially and finally also. So since we are using DFS, there would be recursive stack calls. So I have drawn here the recursive tree where I will explain each and every call and will update this vector, and finally we'll return this vector of distances. So the code here, let me explain each and every line. So this here we have declared an adjacency list in the form of unordered map, where int represents source node and list of int represents the number of nodes which are mapped to this particular node. So we'll run a loop with the size of the edges given here in the function argument. So we'll run it for the size of edges, and we'll take both nodes and we'll map each node to its on 1 to 1. So the U node would be mapped to V. In the same way, V is mapped to U since it's undirected map graph. So if it would be a directed graph, then the second line would be neglected. So secondly, we'll take a vector of distance which would be initially int max, and we'll call the function DFS, and we'll pass source node. Initially the distance would be 0, and we'll pass distance vector and adjacency list. So this is the function DFS function, which contains node, distance and vector and adjacency list. We'll first update the distance of that particular node with the dist, and we'll look for all the neighbors of that particular node. We'll again pass the function with increasing the distance by 1 and remaining vertices and distance and unordered map of adjacency list. If the distance of that particular node is already smaller than the current one, then we'll skip that particular function. We'll return from that particular call stack. And after lots of recursive calls, our distance vector would be updated, and finally we'll also check after returning from that DFS function, we'll check the particular distance vector. If from all the DFS calls, if any vertex by chance still remains the int max value, it generally means that this particular vertex is not reachable from source node. So we'll update that vertex to -1, and finally we'll return the distance vector. So let me explain this function calls. So initially we'll start from 0, which is source node. We'll call to 1 and 3 from the adjacency list, since 0 has 1 and 3 as an adjacency list, by increasing 1 and 1. So here the first value is node and second value is distance. So we have recursively called both 1 and 3. Again we'll call the function from 1. So 1 has adjacency list 0 and 2. So 0 is already visited and it's already has distance value. So we'll neglect this and we'll again give a recursive call to 2 by increasing the distance 1. So here 1 gives a recursive call to 2 by increasing the distance 1. Again we'll look out the adjacency list of 2. It has 1 and 6. Since 1 is already updated, we'll neglect it and we'll look out for 6. So from 2 to 6, we'll increase the distance by 1 and again we'll look out the adjacency list of 6. We have 5, 2 and 7 and 8. We'll give recursive call to 5 initially. So by increasing the distance 1. So 6 gives a recursive call to 5 by increasing the distance 1. So initially the 5 has distance 4. And again we'll look out the adjacency list of 5, which has 4 and 6. So we'll give a recursive call to 4 since it's not visited. So 4 has distance 5, which is incremented by from previous call. So since 4 is completed, we'll again check 6. 6 is already updated, so we'll return back from fifth call. Again 6 has 2. Since 2 is already is in call, so we'll neglect 2 and we'll give a recursive call to 7 by increasing the distance 1. So 6 gives a recursive call to 7 by increasing the distance 1. So 7 has a distance of 4. So again we'll go to 7's adjacency list. It has 6 and 8. 6 is already in the call, so we neglect it and we'll give a recursive call to 8. So 7 gives a recursive call to 8 by increasing the distance by 1. So 8 has distance 5 for now. So 6 for 7 is done and 6 gives a recursive call to 8. So 6 gives a recursive call to 8 by increasing the distance 1. So for now 8 has 4. Here you can observe that previous call has 5 distance and for now the distance of 8 is 4. So we'll update the distance of 8. So finally the distance of 8 from the source node is 4. So we'll consider this distance as we need to find the shortest path from the source. Meanwhile, after completing 6, we'll return from this function call and we'll reach to the main source node. So from here we'll give, since 0 adjacency list 1 has completed, we'll go to 3. So 3 has adjacent values 0 and 4. Since 0 is already finished, we'll go to 4. So 3 gives recursive call to 4 by increasing the distance 1. So 4 has distance 2. So we'll go to adjacency list of 4. 3 is already is in the call, so we'll give a recursive call to 5. So 5 has distance 3. So from 5, 5 adjacency list is already done. So we'll give a return calls to source node and finally our distance vector is updated. So, so the final value of the distances of each vertex from source node would be 0, 1, 2, 1, 2, 3, 3, 4 and 4. So let's submit this code and let's see. It's giving correct output. Let's submit it. As I said earlier, this DFS calls has a redundant paths. As you have observed from this recursive call, it is visiting that particular vertex more than one time. For example, 8 and for example 4 and 5. These recursive calls is reaching and pointing these vertex more than one time. So the time taking for this code would be more. So hence we use BFS approach. In BFS approach we use queue and we'll do the same method of solving this. So this is the BFS code of the same question for finding the shortest path from source to all the vertices. Here I have taken adjacency list in the form of 2D vector, and I have also taken queue. Initially I have pushed the source node into the queue, and I have taken a distance vector, and I have mentioned the distance of all vertices int max initially. The distance of source node would be 0, and we'll run the loop till the size of the queue. We'll pop the current element, and we'll run through all its neighbors. After running all the distance between its neighbors, we'll check whether the distance needs to be updated or not. If it needs to be updated, then we'll update the distance of that particular node, and we'll push that particular node into the queue. And this goes on until or unless all queues are visited and all vertices distance are updated. After finishing and coming out of this queue, we'll once again look out the values of the vector. If any, if by chance any value is still int max, we'll update that particular vertex distance to -1 as it is unreachable from the source node. And finally we'll return the distance vector. The time complexity would be same, O of v plus 1, but the practical time complexity would be less as compared to DFS, as there is no recursive call stacks for redundant paths. Let's compile and run. Let's submit. So as you can see, this approach is successfully submitted. So the time complexity would be O of v plus e. V represents vertices and e represents number of edges, and space complexity would be same. So hope you like this video and explanation. I'll see you in the next one. Thank you.